In this problem, there is a ball which is kept near a step and a force is applied at the center in the direction as shown, and you have to find out the minimum force that should be applied so that the ball gets up the step. Now, this is a tricky problem. Please understand that if the ball is to get into this upper portion, that is, it moves up the step, what is happening? The key concept is that the ball loses contact with this bottom surface. And when something loses contact, what happens? The normal reaction force at that contact becomes equal to 0. This is the fundamental concept based on which this problem would be solved. Everything else is easy, okay? So let's draw the free body diagram of the ball. So this is the ball, a little rough diagram. The weight is acting downwards, which is equal to mg. There is a normal reaction force at the bottom. Both of these forces are along the same line, but given my drawing, they look a little separated. There is also another normal reaction force which is acting at this point. This is at the point P. Let us call this as N2. There is this force F which is acting at this point. Is there any other force? No. So what you have to do is you have to find out the situation when, or the minimum value of force when this N becomes equal to 0. Let's give some angles, okay? The angles are not given. What is given is this length. This length A is given. I will put that at the end. As of now, let's give some angles. Let us call this as theta. The radius of the ball is equal to capital R. This red color dotted line that I have drawn over here, let me color that as yellow. This yellow colored line, that portion has a length of R sine theta. That would be useful, okay? Let's get on with it. So if I take the moments that are acting on this ball about this point P, what should I get? Since we have to find out the minimum value of the force, we should understand that the angular acceleration of the ball is minimum, which is 0. So there is no angular acceleration, but the moments given by these forces should be such that the ball just steps over. So if I take the moments of these forces about this point P, N2 will not have any moment because it is passing through the point. What else? Mg would have a moment. Mg is trying to rotate the ball in this direction. This capital N is trying to rotate the ball in this direction. The force is also rotating the ball in this direction. So if N are moving in the clockwise sense, Mg is trying to move the ball in the anti-clockwise sense. What is the moment of Mg? That should be Mg multiplied by the perpendicular distance of the line of action of Mg, which is nothing but this length, which we have just found out. So mg times r sine theta is the moment given by mg. What about n? N is also acting along a line which is at the same distance r sine theta. So mg minus n r sine theta. What about the moment given by the force? So the force is acting along a line which is at a distance of r. So the moment given by the force F is also minus F into R. Why are these minus? Because I have taken the anti-clockwise sense as the positive direction, and this must be equal to 0. Okay, now understand. When the ball loses contact with the surface, N becomes equal to 0. This term would be equal to 0. That means mg r sine theta must be equal to capital F times R. The R cancels out and I get F is equal to mg sine theta. Now see, the theta is not given. After that, it becomes a geometry problem. You have to find out the value of theta. How can you do that? it's given that this length is equal to A. That means, let me give some names. Okay, let's refer to the bigger diagram on the left. So basically I have taken this as theta, the center is O, this contact point is given as P. Let me name this point as A. That means sine theta is equal to AP by OP. Now see, OP is nothing but R. What about AP? AP needs to be found out. AP is OP square minus OS square. Let me write it over here. Root over of OP square minus OS square. Now again, OP is R square. What is OA? OA would be R minus this length, which is A. So this means this is equal to R minus A whole square divided by R. Complete the mathematics. This would be equal to R square minus S square plus twice AR divided by R. These two cancels out and you are left with twice AR minus S square divided by R. Put it over there and you get force is equal to mg times root over of AR minus S square divided by R. So this problem is done. It's a little bit on the tougher side, I should say, little bit higher than moderate, and that is because of a few understandings that are required over here. That is, the normal reaction at this point becomes equal to 0, and also the fact that the force is minimum. That means the angular acceleration must be nearing to 0. You just need to balance the forces and find out the condition when the normal reaction becomes equal to 0, and you get the answer. Okay, thank you.